Every modern fighter jet is built on one basic idea. It needs a tail, not for looks and not out of habit, but because without it, the aircraft becomes inherently unstable, harder to control, in certain flight regimes, almost impossible to fly safely at all. That's not a theory engineers debate. It's a constraint they design around. So when images started circulating in late 2024, the reaction inside defense circles wasn't excitement. It was confusion. Two Chinese aircraft appeared around the same time. Different sizes, different configurations, but they shared one detail that didn't make sense. They had no tails, no vertical stabilizers, no conventional control surfaces where you'd expect them. At first, it was easy to dismiss. A test article, maybe a design study, something experimental that wouldn't go far. But then more footage surfaced, different angles, additional flights, independent sightings, and the detail that seemed like a one-off kept repeating. That's when the reaction shifted. Because removing the tail on a high-performance aircraft isn't a minor design choice. It's a fundamental trade-off. You're giving up something critical, stability, in exchange for something else that has to matter more. And that's the part that wasn't immediately clear. Why take that risk? What exactly do you gain that justifies removing one of the few features every modern fighter depends on? Because if this isn't an experiment, and the evidence increasingly suggests it isn't, then this isn't just a new aircraft design. It's a different set of priorities. And if those priorities are right, then the way air combat is being optimized may already be changing. To understand why China is removing the tail at all, we have to start with something much more basic. What the tail actually does. On a conventional fighter, the vertical stabilizers are doing constant, quiet work. They keep the aircraft pointed where it's supposed to go. They correct small disturbances before the pilot even notices. They give the jet directional stability, especially at high speed, high altitude, and during aggressive maneuvers. Take that away, and the aircraft doesn't just become less stable, it becomes actively unstable, which, on paper, sounds like a terrible idea. And for a long time, it really was. Designers avoided fully tailless high-performance aircraft because the trade-offs were too severe. You could reduce drag and radar signature, sure, but you paid for in control, predictability, and pilot workload. That's why even stealth aircraft like the F-22 or F-35 still keep vertical tails. They're carefully shaped, minimized, and angled, but they're still there, because removing them entirely crosses a line most designs don't come back from. So when these Chinese aircraft showed up without tails, the first assumption wasn't that they had solved the problem. It was that they had accepted a compromise. That maybe these were specialized platforms, limited roles, not true frontline fighters. But that explanation starts to break down when you look closer. The configurations aren't crude. The shaping is deliberate. The surfaces are clean in a way that suggests this was an afterthought. It was a starting point. And more importantly, there isn't just one design. There are at least two moving in the same direction. That's not experimentation anymore. That's intent, which forces a different question. What changed make this viable now when it wasn't before? Because the physics haven't changed. So something else must have. The more analysts looked at these aircraft, the harder it became to fit them into a familiar category. One of the designs, larger, broader, almost stretched, doesn't behave like a traditional fighter at all. The proportion suggests something built for range, for carrying more internally, for staying in the air longer than most frontline jets are designed to. That's unusual, because when most people hear next-generation fighter, they picture something faster, more agile, better in a dogfight. But this doesn't point in that direction. If anything, it points away from it. On paper, removing the tail should make maneuvering harder, not easier. You're giving up natural stability, which pilots rely on during aggressive turns and high-angle maneuvers. So, if agility isn't the priority, then what is? This is where the design starts to feel less like an upgrade and more like a shift in purpose. The layout suggests a different kind of mission profile. Longer reach, more internal fuel, more space for sensors or weapons that stay hidden inside the airframe. And that leads to an uncomfortable possibility. What if this isn't meant to win close-range fights at all? What if it's designed to avoid them? Because in a modern, missile-heavy environment, the fight is often decided before aircraft ever get close enough to see each other. Detection comes first. Targeting comes next. And by the time maneuverability matters, the outcome may already be locked in. That changes the value of everything. Suddenly, being harder to detect matters more than turning tighter. Being able to operate farther out matters more than sprint speed. And carrying more internally, fuel, sensors, weapons, starts to define what the aircraft can actually do. if that's the logic behind these designs, then removing the tail isn't just about stealth. It's about shifting what the aircraft is optimized for. But there's a problem with that idea. Even if you accept the trade-offs, there's still one major hurdle left. You've removed the very thing that helps keep the aircraft stable. So what's replacing it? This is where the conversation usually goes wrong. Most people focus on what's visible, the shape, the missing tail, the clean lines. But that's not the real breakthrough. The real story is what has to happen behind the scenes to make that shape fly at all. Because once you remove the tail, you're not just changing the aerodynamics. You're removing the aircraft's built-in ability to stabilize itself. And that means something else has to take over that job. Not partially, completely. In modern aircraft, that something is software. Flight control computers are already doing a lot of the work in jets like the F-22 and F-35. They constantly adjust control surfaces faster than any human could, smoothing out instability and translating pilot inputs into something the aircraft can actually handle. But those aircraft still have tails. They still have a safety margin built into design. Take that away, and the system has to do much more than assist. It has to replace stability entirely. That's a much harder problem. Now you're relying on continuous, real-time corrections just to keep the aircraft flying in a straight line. Every movement, every disturbance, every change in airflow has to be managed actively. And if the system lags or fails, the aircraft doesn't just become harder to fly, it becomes uncontrollable. That's the risk. But it also explains the payoff. Because once you accept that level of instability, you unlock design freedom that wasn't possible before. You can eliminate vertical surfaces that reflect radar. You can smooth out the entire airframe into a shape that's harder to detect from almost every angle. You reduce drag, which improves efficiency and range. And you gain internal space. Space that can be used for fuel, sensors, or weapons that stay hidden instead of hanging externally. On paper, this sounds like a perfect trade. Better stealth, better range, more internal capacity. That's the idea. But there's a catch. Actually, several. First, control becomes extremely complex. You're no longer working with a stable platform. You're constantly managing instability. Second, the control surfaces themselves become a problem. On a tailless aircraft, you often need more of them, not fewer. Small flaps, segmented edges, subtle movements across the wing to replace what the tail used to do. And every time those surfaces move, they risk disrupting the very stealth profile the design is trying to protect. So now you're balancing two opposing requirements. Stay invisible and stay controllable at the same time. That's not an easy balance to get right. And this is where things get more interesting. Because when analysts looked closer at these Chinese designs, they started noticing something unusual. The trailing edges aren't simple. They're segmented, broken up into multiple control surfaces that can move independently. That suggests a level of control complexity beyond what's typical. Almost like the aircraft isn't relying on one solution, but several working together, which raises a different possibility. What if the tail isn't being replaced by a single system, but by a combination of control surfaces, thrust vectoring, and software all working at once? If that's true, then the real shift here isn't just aerodynamic, it's architectural, and it suggests something bigger. These aircraft aren't just redesigned, they're being rethought from the ground up. And if that's the case, then the question isn't just whether they can fly like this, it's whether they can operate effectively in combat like this. Because that's where the real test begins. Up to this point, this could still be seen as an engineering story, a bold design choice, a difficult technical problem, maybe even an over-optimization of stealth. But the moment you place this aircraft into a real-world scenario, the logic starts to sharpen, because geography changes everything. The Pacific isn't a forgiving environment for air power. Distances are enormous, bases are spread out, and one of the most critical pieces of the entire system, the tanker fleet, is both essential and vulnerable. That's the part that doesn't get much attention. Modern air power, especially for the US and its allies, depends heavily on aerial refueling. Fighters don't just take off, fight, and return. They rely on tankers to extend their range, keep them on station, and allow operations far from home bases. Remove the tanker, and the reach of those aircraft shrinks dramatically. That's a known weakness. And if you're designing an aircraft specifically for this environment, you don't necessarily need to outturn your opponent. You need to outlast them, or reach further, or operate where their support systems can't safely go. Now, the tailless design starts to make more sense. Less drag means better efficiency. Better efficiency means more range. More internal volume means more fuel carried inside the aircraft itself, without compromising stealth. And if the aircraft can operate farther out, with less reliance on tankers, it changes the dynamics of the entire battle space. It allows missions that stretch beyond the traditional limits of fighter operations. It creates pressure on support assets that were never meant to be directly threatened. And it complicates the assumptions that current air strategies are built on. That doesn't mean this aircraft is automatically superior, but it does mean it's solving a different problem. And that's where the real ship begins. Because if one side is optimizing for dogfights, and the other is optimizing to avoid them entirely, then they're not really fighting the same war anymore. And that's a much harder problem to answer. At this point, the pattern is hard to ignore. This isn't just about removing a component. It's about removing a constraint. For decades, fighter design has been built around a compromise. You accept certain shapes, certain surfaces, like the tail, because they make the aircraft stable, controllable, and predictable. And then you try to hide them. You angle them, shrink them, shape them to reduce radar returns. But they're still there, and they still come with penalties. Radar reflections, drag, limits on how clean the overall airframe can be. What these designs suggest is a different approach. Instead of managing the penalty, remove it entirely. On paper, that sounds like a breakthrough. No vertical surfaces, reflecting radar, a smoother, more continuous shape, better efficiency, more internal volume, more range. That's the upside, but only if everything else works. Because what replaces the tail isn't simple. It's a combination of software, control surfaces, and possibly thrust vectoring, all working together constantly just to keep the aircraft stable. And that introduces a different kind of risk, not aerodynamic, systemic. If the control system struggles, if the integration isn't perfect, if the aircraft can't maintain stability under real combat stress, then the advantages start to fall apart. And that's the part we still don't have answers to. There's no verified performance data. No real insight into how these aircraft behave in complex, contested environments. So for now, a lot of this sits in a gray zone. Promising but unproven, and that matters, because it keeps the story grounded. This could represent a genuine shift in how air combat platforms are designed. Or it could turn out to be a design that works in theory, but struggles in practice. But even with that uncertainty, one thing is already clear. The priorities are changing. This isn't about building a fighter that turns better. It's about building one that is harder to detect, can operate farther out, and fits into a larger system where information, coordination, and reach matter more than raw maneuverability. And if that direction holds, then the aircraft that defines the next generation of air combat won't be the one that wins the closest fight. It'll be the one that's hardest to find, and the one that shapes the fight before it even begins.